conduction and convection. We talked a little bit about what heat is, heat transfer, but now we're going to talk about radiation. If you've heard the word radiation before, you may be thinking about nuclear energy, Homer Simpson, Fukushima, nuclear bombs, gamma radiation, and so on. But actually, radiation is much more common than you would think, and it's not nearly as scary as you would think. Now, sure, nuclear power plants and nuclear bombs, like that's a type of radiation, or they emit a type of radiation. But you're going to be surprised what else emits radiation and how present radiation is in our everyday life. So let's jump in and talk about it. So our first goal for today is to understand the key properties of radiation. So what makes radiation what it is, and what types of radiation are there? And then we're going to talk about a few key laws that help define how temperature affects the type and amount of radiation that an object emits. And we're also going to talk about what kind of objects emit radiation. And then we're going to end this lecture by talking about the difference between solar radiation, which is given off by the sun, and terrestrial radiation, which is given off by the Earth. So let's jump in. So first off, what is radiation? Well, the last lecture we talked about conduction, which requires a solid object for heat to travel through it, and convection, which requires a fluid for heat to travel through it. Well, radiation is different. Radiation represents the transfer of energy in the form of what are called electromagnetic waves. So basically beams of electricity and magnetism. Radiation is a little bit different from conduction and convection in the fact that radiation doesn't need anything to travel through. It doesn't need a conductor. It doesn't need a fluid. It can travel through those things, but it doesn't need them. Radiation can travel through a vacuum. It can travel through empty space, which is a good thing because that's how light gets from the sun to us. So, yay, radiation doesn't need anything to travel through. But radiation can travel through other things as well. It can travel through air, hence our atmosphere. It can travel through water, and it can travel through empty space. It can travel through solid objects. There are many things that radiation can travel through. And different types of radiation can travel through different objects. We're going to talk more about that in the next lecture when we talk about what are called selective absorbers. But for now, let's talk a little bit more about how radiation works. So, there are three key properties of radiation, and the three properties are wavelength, frequency, and energy. With that said, wavelength is really the most important and key defining property. In fact, frequency and energy are simply determined by the wavelength. So let's talk about what the wavelength is. If you were to zoom in on a beam of radiation, you would see something that looks like this. This is what's called a sine wave. A sine wave is just a wave that uniformly goes up, peaks, goes down, bottoms out, goes back up and peaks again, goes back down and bottoms out again, and so on and so forth. Well, the distance between any two consecutive peaks is what we call the wavelength. And us weather people, we love to use the Greek letter lambda to represent wavelength. I'm not going to expect you to use it, but I just wanted to mention it so that if you see it in the textbook, because it is in there, or if you see it in other lectures, that just means wavelength. So don't be afraid of it. It just means wavelength. With that said, how do we measure wavelength? Well, a beam of radiation is really, really, really tiny. And in fact, the wavelength is so tiny that many of the units that we normally use, such as feet, inches, miles, kilometers, meters, centimeters, and so on, really don't do it justice. We need to zoom in and look at a much smaller unit. And the unit that we use in particular is what's called the micrometer. So think about a meter, which is about 3 1/4 feet. So it's about the size of I would say the best thing is, or the best estimate is, think about the length of one of your arms, maybe a little longer than that. Well, a micrometer represents 1/1,000,000th of that meter. 1/1,000,000th. That is extremely thin. In fact, if you have a sheet of paper, that sheet of paper is many micrometers thick. So this is extremely tiny. And this is what we use primarily, our primary unit for wavelength. With this said, as I mentioned, the type of electromagnetic radiation is determined by the wavelength. Now, all radiation isn't created alike. There are some radiations with really long wavelengths. And I'm talking meters and meters in distance. And then there are others that are really, really tiny with really, really tiny wavelengths. And that wavelength determines two other things: the energy and the frequency, which are inversely related to the wavelength. When wavelengths are really high, frequency is really low. And if you think about this, if you took a piece of paper and drew one wave on it, your frequency would be 1. If you were to take that same sheet of paper, but now draw 2 waves on it, you would have 2 waves. That means it's a more frequent wave. But if you were to measure the distance between those 2 peaks, it would now be half the size of the initial wave. So, lower frequency. And as a result, less energy. On the other hand, if you have very short wavelengths, the shorter the wavelength, the more frequent it is, and the more energetic it is. So, longer wavelengths, lower frequency, less energy. Shorter wavelengths, higher frequency, more energy. And we can actually peek at this a little bit by looking at what's called the electromagnetic spectrum. This is basically the gamut with which radiation runs. You can start with very, very, very short wave radiation, such as X-rays, which are able to pierce our skin, get absorbed by our bones, and actually show a doctor how our skeletal system looks like. So these are very powerful. To AM radio waves all the way up here, which are very long waves, and lead to what I would consider to be a pretty dismal radio signal. And everything in between. And these are just common things that we see in our everyday life. X-rays are used by doctors to look at our skeletal system or look at what's going on in our internal organs. UV radiation, this is the stuff that you want to protect yourself from when you're out in the sun. This is what can give you sunburn, can cause skin cancer. Visible light, this is what our eyes are sensitive to, and hence it registers to our brain as colors. Infrared radiation, this is the kind of radiation that the Earth emits, and it's also the kind that kind of gives you that warmth, but it's not really dangerous. Microwaves, these are particularly, or water molecules are particularly sensitive to these, and water molecules absorb them very well and vibrate. This is how microwave ovens work. And cell phones actually use a type of microwave radiation as well. And then there's television and AM radio waves. But what I just want you to know here is that the longer the wavelength, the lower the energy. These AM radio waves pass through our bodies harmlessly. Whereas UV and X-rays, when they pass through our body, they can actually cause some harm. They can actually do some damage. It's one of the reasons why when you go to the doctor and they're taking an X-ray, they put a lead vest on you. With that said, there's a few key laws that I want to discuss when it comes to radiation. The first law is actually more of a fact, but an easy way to remember it is by calling it what I like to call Oprah's Law, and I'll explain why I call it that in a minute. Then there's Wien's Law and the Stefan Boltzmann Law. So let's talk about these laws real quick. The first law, Oprah's law. Oprah's law states that every object imaginable with a temperature above absolute zero emits radiation. And I call this Oprah's law because this basically means everything you see around you, the chair you're sitting on is emitting radiation. The table that your computer's on is emitting radiation. If you have a phone, that phone you're holding on to emits radiation. The clothes you wear emit radiation. This also means that you emit radiation. And that's why I jokingly call it Oprah's law. Because you emit radiation, and you emit radiation, and you emit radiation. Everybody emits radiation. So that's why I call it Oprah's law, because everybody emits radiation. And everything emits radiation. However, that doesn't necessarily mean that we're all glowing or that we're all radioactive necessarily. It just, well, I guess by definition, it kind of does mean that we're radioactive. I mean, we emit radiation. But what kind of radiation do we emit? Well, the next two laws will explain what kind of radiation we emit and what determines the type of radiation an object emits. The first law is called Wien's law. Wien's law was discovered by a German physicist named Wien, and he states that the wavelength that an object emits depends on the object's temperature. And here's how it works. Wien's law states that the wavelength most commonly emitted by an object, that's this lambda max right here, equals 2,897 divided by the temperature in Kelvin. I don't want you to stress about calculating this. You don't need to stress about memorizing that number. Here's what I do want you to know, though. The warmer the object, the shorter the wavelength. The warmer the object, the shorter the wavelength. And what this means is, as temperature increases, the total wavelength becomes lower and lower and lower. If you were to actually do the math, what you would actually find out is that we emit radiation in the infrared spectrum. Like, we are primarily emitting infrared radiation. If you were to turn off a light, you wouldn't notice yourself giving off any visible light. Why? Because you're just not hot enough. Your temperature is not high enough. So you can tell your friends that your teacher told you that, yes, you are radiant because you give off radiation, but unfortunately you're not glowing because you're just not hot enough. I know, corny joke, but hey, you're going to get more of those in this class. But this can also explain why if you had like a metal rod or lava or something like that, and it gets really, really hot, it starts to glow. Because as it gets hot, the amount of, or the type of radiation that it gives off becomes shorter and shorter and shorter. The wavelength gets shorter and shorter and shorter. And as a result, it begins to glow. It enters that visible light spectrum and begins to glow. On the other hand, what determines how much radiation an object gives off? Well, believe it or not, that's directly related to the temperature. This is what's called the Stefan-Boltzmann law. This law was created by two gentlemen named Stefan and Boltzmann. And this law basically states that the warmer an object is, the more radiation it emits, the more radiation it gives off. Again, don't stress about this equation. Just know that the warmer an object, the higher that this temperature is, the higher the amount of energy the object gives off. So simply put, the warmer an object is, the more radiation it emits. Now with that said, let's talk a little bit about the type of radiation the sun gives off versus the type of radiation the Earth gives off. And then we can also talk about the amount that the sun gives off versus the amount that the Earth gives off. So first thing, let's get straight, let's get clear, is that both objects have a temperature above absolute zero. The Earth has an average temperature of about 280 Kelvin, and the Sun has a temperature of about 6,000 Kelvin. So they're both well above absolute zero. As a result, they both emit radiation. However, the Sun is very hot. With that temperature of around 6,000 Kelvin, it emits a lot of radiation. And it emits it primarily in the ultraviolet, visible light, and near-infrared wavelengths. So the radiation it emits the most happens to fall into these three categories: ultraviolet, visible light, and near-infrared. And this is actually pretty straightforward to know because when you look at the Sun, which don't look at it, but you know that the Sun gives us light. We also have another name for this, and I'm going to use this name for the rest of the course, and you're going to hear this name a lot. So it's a name worth memorizing. We call this shortwave radiation. So whenever I talk about radiation given off by the Sun, I call it shortwave radiation. So the Sun emits shortwave radiation. On the other hand, the Earth has an average temperature of around 288 Kelvin, and as a result, it emits a lot less radiation than the Sun, and it emits it in much longer wavelengths, over in the infrared spectrum, very similar to what we as humans emit. We call this long-wave radiation. So the Sun emits UV visible light near-infrared, called shortwave radiation, and the Earth emits infrared radiation, and we call this long-wave radiation. So most of the radiation that the Sun emits actually falls under the visible light category, and that lambda max, the wavelength most emitted by the Sun, actually happens to be here in the orange, yellow, green, blue category. It also emits a lot of red and purple, but this happens to be where the Sun emits most of its radiation. It emits about 7% in ultraviolet, 37% in near-infrared, and then less than that over here. So again, most of what the Sun emits, most of that shortwave radiation, is in the ultraviolet, visible light, and near-infrared. On the other hand, the Earth, with a temperature of 288 Kelvin, emits a lot less radiation. You notice that this peak here is a little bit, much lower, and it emits it in substantially longer wavelengths. And so this is long-wave radiation. Well, how does the Sun affect the Earth's temperature? Well, this is actually pretty simple, and this is a graphic that I drew back in grad school, and I was so proud of it that I just kept it. Obviously, you can chuckle at that because this is just from Microsoft Paint, but it gets the job done. So we have our Sun with a nice temperature of 6,000 Kelvin, very hot, and it gives off all of this shortwave radiation. The shortwave radiation then reaches the surface of the Earth, which then absorbs it. And as the Earth absorbs this radiation, it heats up. As an object absorbs radiation, it heats up. So now the Earth here is heating up. Its surface is heating up, and as a result, by Stefan Boltzmann law, it emits more radiation. So basically, the whole process works like this. Sun emits shortwave radiation, Earth absorbs that shortwave radiation, heating up, and then it gives off more long-wave radiation. Now, what would happen if somehow, some way, the Sun suddenly became dark and it stopped emitting shortwave radiation? Well, the Earth, because it has a temperature above absolute zero, is still going to emit long-wave radiation. But since it's not receiving any additional shortwave radiation, it's going to result in a net loss in radiation. So it's losing more than it's giving. This happens every night, and that's why temperatures are cooler at night, because the Earth is giving off more radiation than it's getting. But we can even see this on a much shorter time scale through something like the solar eclipse. So last year I had the privilege of going up to Oregon to witness the Great American Solar Eclipse. And basically what happened was the sun rose around 6:30 that morning, and I happened to get into the path of totality. And what actually happened was right around 9:15 in the morning, the eclipse began. As the eclipse got stronger and stronger, as it came closer and closer to totality, the amount of solar radiation reaching the surface of the Earth declined substantially. And then when totality occurred around 10:20-ish in the afternoon, or in the morning, around 10:20-ish in the morning, incoming solar radiation dropped to approximately 0. Interestingly enough, at the same time, air temperature in that same location dipped a little bit. Normally what happens is as the sun comes out, which the sun came out here around 6:30, you begin to see an increase in air temperature. But in this case, because the solar eclipse was happening, the moon was shading out the sun, we had less incoming radiation, and so Earth cooled a little bit. And then as soon as totality was over, incoming solar radiation quickly picked back up, and air temperatures recovered and went back to normal summertime temperatures. But this is just a cool example of what can happen during an eclipse. We're going to talk more about this energy budget in our next video when talking about how Earth handles all of this incoming radiation. So until then, I'm Terrence Mullins. Thank you for watching.